Hello everyone and welcome to our next webinar of Würth Elektronik. So I'm very happy to welcome all of you and that you took the time today to participate in our webinar. My name is Markus Eberle and I will moderate this webinar today, but very more important, Dominik Zeller today is here. Dominik, hi. Welcome.
Hi, thank you for letting me join to this webinar.
Yeah, of course. I'm looking forward to it.
Yeah.
So, Dominik will talk today about the presentation and also answer your questions after the webinar. And the topic today you just take part is EMC with EMC. And I'm also very curious about this topic. And also there was one question in your introduction to this topic with the bees and the flowers. And I'm really curious about because I always order this topic to another scene.
In English you would say something with bird and the bees. But in this case, we are going to stay family friendly. So don't be scared.
So that's all from my side. We will see us later. And then, Dominik, stage is yours.
Thank you.
Enjoy.
Superb. Then I will stand in the middle so you guys can see me at least a bit better. Yes, EMC with EMC, or Electromagnetic Compatibility with Electromechanical Connectors. What are we going to talk about today? Well, first we will have a short introduction into the topic of EMC. We will then speak about coupling effects. What are coupling effects? What sort of coupling effects can occur? And then we will speak a bit about layout concepts, signal integrity, and the last part will be shielding. Okay, then let's jump into the first topic. Well, the first topic is going to be why are we even talking about EMC? Well, because it's mandatory. There's a law and we have to apply this law onto our application. In other words, there are many phenomena like radiated immunity or radiated emission, contacted immunity if something is on the cable, and ESD. And all of those things are in this EMC environment. And we are always in an EMC environment, except if we are in an EMC chamber, because we are surrounded by electromagnetic waves, radio, Wi-Fi, all sorts of things. And all of those things can disturb our application or our application is disturbing those other applications. And this is not allowed. And there is a rule. Sorry, but this slide is going to be in German, but it doesn't matter because it's just a short introduction regarding the EMC guideline in Austria. You in your country have, of course, a suiting law, and this is really comparable because the thresholds in Austria are the same in Spain. Otherwise, that would be quite unfair if we Austrians would have it easier than you guys. What do we also need? Well, we need an EMC lab. Simply put, it's just a really big metallic case. And you stand in the middle, or in this case inside, and you are surrounded by ferrite sheets and absorber materials. Why? Well, you only want to see your application and not all the other electromagnetic waves due to radio or Wi-Fi. And those absorbers have the main reason for them is to absorb, or in this case, to not reflect the signals, because you only want to see the original signal and not all of the reflections that may occur. Yes, in this case, it's a picture from Würth Elektronik High Innovation Center in Freiham. Freiham is near Munich. Superb. Well, I already talked about thresholds, and we have a range where we have to measure. In this case, if we speak about conducted emission, it's currently 150 kilohertz up to 30 megahertz. This will change in the future. We will probably have to go lower than 150 kilohertz. Why in this range at all? Because in this range, most of the noise is going to stay on the cable. The antenna effect, starting at 30 megahertz, going up to 1 gigahertz. Here we have to measure all the radiated emission. 1 gigahertz, well, sometimes 3 gigahertz, 6 gigahertz, really highly depending on the application. Military applications up to 18 gigahertz, 30 gigahertz, and so on. And of course, we also have different thresholds for industry and for consumer. Consumer are going to have a lower value they have to reach, and in industrial environments, due to the higher amount of noise, you have it a bit easier. So, what does everything, or in this case EMC, has to do with flora and fauna, or in this case with bees and flowers? Well, when a bee travels along, or in this case flying, due to molecular friction, it loses electrons. Therefore, it's positively charged. And even though the flower is rooted to ground, in this case through roots, an electric field is going to build up. It's highly depending on the environment, so if it's really dry, the voltage is going to be higher, and also highly depending on the flower itself, so the geometry decides a bit how high the electric field is going to be, and the height of the flower. But as a rough estimation, 1 meter of flower would be about 100 volts. So what happens when the bee lands on the flower? Well, we have an E field, and it's on the top, on the maximum level. So it's more negatively charged. And if you have something positive and negatively charged, and you put them together, ideally, the E field that is going to be created will be 0. So it will cancel each other out. What is the benefit for the bee and for the flower? Well, due to electrostatic discharge, the pollens will really shoot onto the bee and stay there. So pollination for the flower is going to be secured. And for the bee, it's also beneficial. Why? Well, the bee can feel the electric field generated by flowers. And if a bee already landed on that flower, there is no electric field, so the next bee that's coming is not going to land there. So it's an energy saving mode, to put it simply. And that's exactly what we do in the EMC environment. We try to cancel out fields. Of course, it's a really simple explanation. Why? Well, first of all, the electric field that's going to be generated is quite small. We don't have flowers that generate up to 200 kilovolts, because then we would have a field full of dead bees. And it's a static field, so there is no change in the electric field, which is not the case in most circuit boards. So, what coupling effects do we have? Well, when we speak about coupling effects, first of all, we always have the electromagnetic wave. In the near field, one is more dominant, either the electric field or the magnetic field. And if the electric field is more dominant, then we speak about capacitive coupling. Meaning we have two conductors, they build up kind of a parasitic capacitance, therefore you have electric field and you have coupling. On the right side, or in this case on the bottom side, you will see typical values for, let's say, optocouplers from 1 to 5 picofarad coupling capacity. we also have inductive coupling. Inductive coupling is going to be generated by a magnetic field that induces current into a nearby conductor. Induces current into a nearby conductor means also if there is no nearby conductor, well, you will have no current. So, of course, space between those two things matter. And you probably heard of that one too, impedance or galvanic coupling. This occurs if two signals have the same return path. Then they can disturb each other. We will see later on what that means. It's a bit cryptic. And then if you go to the higher technical college in Austria, in the first year, you will learn one pretty simple rule. Current will always go the path of the least resistance. That's true, but only for DC current. As soon as you make things more complicated, and in this case, introduce frequency into the formula or equation in this case, yeah, things change. In this case, the current will take the path of the least impedance. And this is always directly under the transmission line going in one direction and back, well, yeah, directly under. This will only work if we let current, or in this case the electric field or the electromagnetic fields, do their job. If we, well, create loops, unintended or intended, current will have to find a new way. Most often, it's not the path we want to have. In this case, yeah, it will find a path where it will probably create the most issues for you guys. Yeah, that's at least what I saw. And the real big problem is that in our head, DC current makes a lot of sense. And therefore, we always think in DC current. So if the distance is quite small, of course the current is going to go the short direction and not the complete way around something else. But that's not the case. And we did get a lot of questions regarding when is frequency, or in this case, how much frequency do you need in order that the current is going to be directly under the conductor. And we made simulations with Cybersdorf, that's an Austrian EMC lab. And here you can see, what do you see? Well, you see the orange thing, that's our complete ground plane. And on the top, you will see the U-shaped conductor. So in our head, if we apply current, well, it's going to go the direct way and back out of the system. But that's not the case. And when does that happen? Well, between 500 Hertz and 1 kilohertz. So in this area, current is going to change from the direct path to the path directly under the conductor. So even though you think it's a small, slow signal, always be aware of your return path. And don't make any cutouts. Well, for house installations, all those things don't matter. Why? Well, because we have up to 200 Hertz. No problem with that, because here it will take the path of the least resistance. Yeah, superb. You could also measure that with a near field board. In this case, in every rectangle you can see there's a really, well, sort of bad near field probe. What do I mean with bad? It only measures the really near field. And by that you can see the outcome of the magnetic field that's going to be generated due to the cutout. The circuit board itself is quite simple. It's the easiest version you could create. The bottom side, the big one, is a complete full ground plane. Well, not completely because we have that cutout. And on the top, connected with pin headers and socket headers, we have a transmission line. Also one circuit board with full copper. But what do you see now? Well, you see something really nice when you do change to the 3D view. You see we have no field in this area. Also nothing in that one. What happened? Well, here we have the transmission line directly over our ground plane. So the generated magnetic fields can cancel each other out. And they will so, only if we let them. Yeah? Here the cutout is seen in red, is quite an intense magnetic field. And coupling should be reduced to a minimum, especially if you have a loop. Why? Well, a loop is nothing else than a loop antenna. And an antenna is really good in receiving and sending a signal at a certain frequency range. Now comes the really freaky stuff, where most of you electronical engineers will say, well, EMC is like magic, wizardry, and witchcraft. What you can see is now the current flow on the ground plane. So we have our transmission line going down through the pin and socket header to my ground plane, and you can see clearly, of course, current has to go on the outer shape. But what you also see is you have current in the inside. Now you have smaller current in this area and you have nearly the same current as here. What happened? Well, at first we thought, yeah, easy explanation, capacitive coupling. And then we realized, well, the signal is a 1 megahertz square wave, and at that frequency range, you would need a massive capacitance to have capacitive coupling. So what happens is you have eddy current. Eddy current inducing a flow in the other direction. And why is it bigger in this area than in this area? Well, because in this area we have the top transmission line, like seen here. This part is also inducing eddy current on the bottom ground plane. And to be quite frank, that's the easiest setup you can imagine. We have no active parts, we have nearly no parts at all, and we already have a lot of confusing stuff going on. And that's always the hard thing about EMC, is breaking it down to the most simple effects like capacitance, inductance, and fields. So what could we do to reduce crosstalk? One very efficient thing is to just increase the distance between two traces. In this case, there's this general rule where you increase the distance by a factor of 3 with the substrate thickness, and you reduce the crosstalk to 1%. You also see very often those via fencing or ground fencing. Yes, they work, but be aware that increasing the distance will reduce the crosstalk way more than this ground fencing or via fencing, however you want to call it. And also be aware that the vias have to be placed in a certain distance. So most often you see lambda divided by 10, and yeah, please please apply that rule. Another thing which is really freaky is what happens if we change layers. So again, a 2-layer circuit board. We have on the left side, the orange thing, a transmission line that is not changing the layers at all. And we have one where we have changing from the top to the bottom and then staying on the bottom for a certain amount and then going up again with vias. Well, if you look cross-section, you have top, bottom, and then again top. You created a loop. The first thing is for RF current, it doesn't matter what return path it's going to choose. It's going to choose the next one that is in the near vicinity. So this means for the return path, it will change layers and it will travel on the VCC plane. Could create issues. However, the bigger problem is the radiated power will also double. If I switch quite fast, you will see the fields generated are going to be bigger. So, of course, we cannot avoid vias. I mean, we can certainly not avoid it with 2 layers, nor 4 layers, nor 6 layers. But what we can do is, if we have a signal that's traveling really fast on a transmission line, there we should avoid vias at all costs. And then we go to the analog part or the slower digital circuitry and place them there if needed, and only if they are needed. Yeah, then we have layout concepts. Generally speaking, there are 3 steps you can do to improve your EMC behavior. The first thing is, and that's probably the hardest one, is improving your layer. Why is it the hardest? Well, there's one problem and many solutions. And sometimes solutions promoted on the internet are not true, but worked for a specific application. Meaning, in your application, sometimes things that should work won't work. And that's quite annoying. Yeah? The second thing is that's that part where Würth Elektronik is starting to smile is when you need filtering. Why do we smile? Well, you need parts from our portfolio. And the third part is going to be shielding. Yeah? Shielding is the last thing you can do to pass the EMC test. And what we see in Austria is often that the steps are not correct done. Meaning, you go to the EMC chamber, you fail the EMC test, you panically attach shielding onto your application and try to somehow pass the EMC test. First of all, shielding sometimes brings between 30 to 60 dB. If you are, I don't know, 70 dBs above the threshold, you will have problems. That's the first problem. And the second problem is shielding is really expensive. And I don't mean by the actual components, but by the additional manual labor. Attaching copper tapes or aluminum tapes onto your casing or your connectors is going to be most often a manual labor. Manual labor costs a lot. We try, at least in our layout step, to reduce the amount of THD products and use more SMD products. And with shielding, yeah, we increase the costs dramatically. Yeah. What's the second worst thing about layout concepts? Well, there is no universal truth. Sometimes it can work and sometimes it won't work. Yeah? And that's always the hardest thing, giving tips regarding those matters. Some things are generally more true, and I will show them in this presentation. First of all, well, on the left side you see the bad design, and on the right side the better design. Why is it the left side bad? Well, you can see clearly there are a stack up of more than one circuit board, all connected via, I don't know, flat ribbon cables. And if I have a noise on this cable, it will affect all the other circuit boards. Theoretically, if it only goes this direction, we will have less problems, but capacitive coupling, magnetic coupling, you don't know which is going to be the path of the least impedance, therefore avoid those stack-ups. Better this case. If we have some problems on the cable due to the ground plane, it will hopefully go the direct way out of your system. So star topologies are really good and are really useful. The same goes with separate analog and digital parts on your circuit board. The next thing is, and that's most often the more tricky one, yeah? High impedance connection. A bit trace on your PCB is an inductor. Even though it has no windings, it has a certain amount of inductance. Yeah? And by that, it's a frequency-depending component. And if the inductance is quite high, well, the outcome is going to be quite bad, because most often high frequency noise is going to choose the path of the least impedance. So some parts will travel the direct way you anticipated, and other parts will go something really odd to the thing you were thinking about. Yeah? Here's a superb simple explanation, or example in this case, filter attenuation. Both are the same components. The only thing we changed is the layout. And what you can see is the bad design and the good design is separated by more than 30 dB. I mean, more than 30 dB. 30 dB is not little, it's a lot. And you did not spend more money regarding better components. So what happens? Well, first of all, we have some small parts of our transmission line going down to the components. This is an inductance. One via is an inductance. So some parts are going some noise is going to go this way, and some parts will say, no, that's way too high for me. I will go the straight way to whatever that's going to be. Yeah? And that's the hard thing to see. Okay, we have an inductance, we have probably some kind of capacitive coupling and some transformer coupling, some magnetic coupling. Yeah, so be aware of that. Sometimes we as a manufacturer are also stumbling upon key nice features about our products we had not intended in the first place. Well, SMD spaces is an example. SMD spaces are mainly mechanical parts. So to fix something to your casing, or more than one bolt to each other. Why is it now also a good low impedance connection? Because we had to plate it with tin. It's tin plated. Why? Well, we wanted to solder it in the reflow oven, and therefore we needed a tin plating. Tin has not a lot of permeability. This means the impedance effect is really low compared to a classic mechanical spacer. Why is that the case? Because classic spacers are most often nickel plated or maybe zinc plated. Both of those materials have a higher permeability than tin. Washer placement is crucial. Why? Well, if you put it between your casing and your spacer, you will, of course, create some kind of bigger impedance. So a few parts are maybe going over it, and other parts are going to travel along your PCB. In this case, maybe your ground plane, and affecting other parts. Another thing, connectors are source of EMC issues. Not on purpose and not actively. Most often they are just transmitting already existing problems. What would be one example? If you put a connector into the socket of your connector, you will create an ESD impulse. You also have common mode noise due to maybe radiated emission, or sorry, not emission, immunity. So all of those things cannot be avoided. You will always need filtering, you will always need shielding. But if your ground concept is quite high, going in the direction of high impedance, maybe your ESD is going to ignore your TVS diode and it's going to your controller. If you add more spacers or better connections, maybe your ESD impulse is going directly over your casing, because that's ideally the least impedance it's going to see. Why do we know that? Well, we often see failing ESD tests, and if we apply or if we attach copper tape onto the connector and onto the casing, so the connection has a lesser impedance than before, we will see most often that they are not failing the test anymore. Another thing is also, don't let your cables tangle around. Yeah? Mount them to your casing. Why? Because the fields that are going to be generated are going to be at a minimum. And also, if you have a current in one direction and in the other, you will create a loop only by the size between those two conductors. So if you make the sizes smaller, the loop antenna effect will be slower. If you twist those cables, even better. It has an outcome. Here you can see an impedance measurement of FFC and CIF setup. In this case, we have a CIF connector on one side, then the FFC cable, and then the CIF on the other side. And we have a characteristic impedance, in this case 126 ohm. And if we are now attaching the cable to a conductive surface via Kapton tape in this case, we will see an influence in our impedance. And this is not only seen by the impedance difference, but also by the electric fields. Another thing is a really cheap one. Cheap solutions are always really nice. We have one problem. We have a USB protocol transmitted over a flat ribbon cable. We have, of course, our VCC trace, we have our ground, and we have D plus and D minus. Most often we have noise on the power supply going in one direction to the source or to the sink, whatever, and going back in the other direction. So our noise is differential. If we would now apply, I don't know, an SMD ferrite, it would, of course, reduce the noise, but sometimes it will also affect your signal integrity, meaning the square wave is not ideal anymore and it's becoming rounded a lot. So what could you do? Well, you could use a common mode choke. The problem with a common mode choke is they are not really working with differential mode noises. So we have to somehow transfer from a differential mode to a common mode. What we can do, and that's quite easy, is add a few lanes. In this case, ground lanes. Yeah? We have still the same, maybe a bit reduced noise, but here and here we see the same noise going in the same direction. If we have coupling, we will see also this noise on D plus and D minus. But now, if we attach a common mode choke onto those D plus and D minus traces, we will reduce the noise and our signal integrity will not be reduced or will not work anymore. Yeah, and that's a really cheap solution. I mean, switching from a 4-pole to a 6-pole in this case is not going to cost a lot. Signal integrity, because I always talk about signal integrity. Signal integrity is a big part in our portfolio because most of our connectors are not designed for high-speed connections. And you guys, you electronic engineers, are always good with finding solutions, awesome solutions, and misusing connectors that are not designed for that purpose, which is, of course, a nice thing. But we try to give you an added benefit, in this case an added service, and we did a lot of S-parameter measurements and impedance measurements for a variety of products. And here, a typical setup, differential pair, PCB, impedance controlled, okay. Then we have the CIF connector, we have the FFC cable, and then again the CIF connector. Superb. if we do impedance measurements, well, we see there is a deviation from the expected 100 ohm differential to up to 126 ohm. Mismatch in impedance means we will have reflections, we will have losses, and how high is always depending, of course, on the application, but also depending on your signal and depending on a few other parameters. The first thing is characteristic impedance is not dependent on the length. It will always stay the same. That's a good thing. The bad thing is if you increase the length, also the insertion loss is going to be increased. And we did measurements and we thought, okay, what is the threshold we want where we say, okay, now the reflections are too much. So we decided it's going to be 20 dB. What means 20 dB means 99% of your signal is going through and only 1% is reflecting. Okay, that's nice. Oh, sorry, that's return loss. So the reflections. The insertion loss is, of course, going to be something else. In this case, you have a certain bandwidth, and the insertion loss we defined with 3 dB. Why 3 dB? Because 3 dB means 50% power loss. Yeah. But all of those measurements give you only a partial answer to your question. And what was the question? The question is often, can I transmit this signal, signal, whatever signal, over your connectors? Well, it's highly depending on what signal you are actually going to transmit. So the first thing we did was we tested it for USB. Why USB? Because the standard is open. And we can look up, or we can check how the eye diagram has to look if we want to have a pass. Of course, depending on the signal speed, or in this case, depending on the USB standard, we have rise times that go up and up and up. USB 2.0, rise time of 500 picoseconds. USB 3.2 Gen 1 and Gen 2 already has a rise time of 50 picoseconds. If you increase the rise time, you will increase the challenges you will see. Yeah? But sometimes it's necessary because the signal speed is also going to increase. What we can now tell you is USB 2.0 will work on all lengths of our FFC cables without any problem. What we can also tell you is with Gen 2, so 10 gigabits, you will have a really hard time trying to transmit that over an FFC cable. Why is this now a useful information for you? Well, simply put, because we can now test all sort of signals. Maybe you want to transmit a certain signal, let's say, I don't know, HDMI over our wire-to-board connectors. Simply put, crimp connectors. Well, we could test it. The only thing we need is the description of the eye diagram, and then we can do the tests in-house. Of course, it's always a bit time depending. My colleague has to do those measurements, but yeah, we will try our best to do that. The next thing, and the last thing in this case, is shielding. Shielding is the last effort to pass the EMC test. If you plan it beforehand, you will of course reduce the chances that you are going to fail the EMC test. Shielding, however, is not going to make all the problems go away. And one really big thing, especially because it also affects the connector side, is be aware of galvanic corrosion. Why? Well, what is galvanic corrosion? If you would, and that happens a lot, would match a gold contact connector with a tin plated connector. What happens? Well, we have gold on this side, following those lines to tin, we will see, oopsie, 0.67 volts are going to be generated between those two metals. So what you basically do is you build a battery. Yeah? And if you have a battery at a certain amount of time, it's going to fail. Why? Because some materials are going to be attacked, and so in this case, I don't know, an anode or a cathode is going to be destroyed, and therefore your battery is going to die. This effect can be speeded up by quite a lot if we introduce salt water or any acid liquid. Yeah? What do I mean by that? We did tests in-house where we made it a gold connector and a tin plated connector, and after I think 128 hours of salt spray test, tin was completely vanished. What is directly under tin? Copper. What is going to react to your environment? Copper. It's going to oxidize, it's going to turn green, so your resistance is going to go, your resistance is going to skyrocket, and also your impedance will have an impact. That meaning, if you build a shielding, you cannot be sure that after a few years your shielding effort is still there, because if you have some kind of galvanic corrosion, maybe your shielding will be reduced or your connection is going to be futile. Be aware of that, please. The next thing is, well, a cable is often an antenna. You have a pass in one direction and you go back in the other direction. If you increase the distance between both cables, what you create is a loop antenna. Yeah? How can we reduce the antenna gain? Well, we could put those cables more together. And ideally, we twist those cables. That only works if you have not two signals going the same direction, because then you would highly increase crosstalk. And if you also want to shield the electric field, you can also attach some kind of conductive material. Okay, and then we have a really simple question that often starts a lot of fights. How would you attach the shielding? One side, no side, one side, or both sides? We will make a short questionnaire, and it's going to be fully transparent. You will see the outcome of this questionnaire.
So, yeah, I just started a poll, and I see the first ones of you are already clicking there. And yeah, you see the answer one is not so, yeah.
Yeah, currently it's not the favorite.
Yeah, not the favorite, exactly.
The first thing I would ask, is there a true answer? Maybe not. A little spoiler.
Yeah.
Okay, this is really a nice outcome, because we already did this poll in the morning session in German, and there we had more on the two-sided side than on the one-sided side. So I made that joke that everyone who clicked two-sided will still get gummy bears and the rest will not. In this case, now I have to switch and say everyone on the one-sided will get gummy bears and the two-sided will not. But it's not that simple. That's a really big problem regarding the shielding. And I will explain it a bit in depth. What could happen or what should happen, and why maybe attaching it on both sides is ideal. First of all, it's highly application depending. Yeah? What does that mean? Well, for certain applications, it's going to be better. For certain applications, it won't help at all. And for specific applications, like in the medical device, the shielding is always a really tricky question on how to do, because most often there is a law against some kind of directly connected shielding. But what we can be certain is, if we do not attach the shielding on both sides, the generated electric field and magnetic field will radiate uncontrolled. So the only happy guy in this case or in this scenario is going to be the cable harness maker. Why? Well, because he can sell you the more expensive shielded cable and has no additional work to do. What happens if you attach it on one side? Well, first of all, it's not one cable you can see here, it's more a cable tree, so more than one cable. The idea is you have some kind of noise current going on your cable. This current will not go over your shielding because it's only attached on one side and current needs attaching on both sides, so it will go directly back on the common ground, creating a big magnetic field. However, the inside and the outside are connected by a capacitance, even though it's a stray capacitance or a parasitic capacitance, however you want to call it. This will short circuit your electric field. So if you attach it on one side, electric shielding will work. In this case, the E-field shielding will work. Now why is in most cases attached shielding on both sides the best choice? Well, first of all, if we have a noise, we will have the same outcome at this point. Current will have to choose the path of the least impedance. What is the path of the least impedance? Well, as near as it's physically possible to your coming or forwarded voltage, or current in this case. Yeah? So the shielding will always be the least impedance the signal will see. Why is this sometimes a problem? Well, sometimes you will create ground loops. And then it would be better to attach it on one side and on the other side with a capacitance. This capacitance will be a short circuit for most higher frequency noises, and all the DC current will not go over the shielding. However, if you only attach one capacitance, you will have some noises that will going over the common ground. And that's the tricky thing when we say, well, there is no universal rule, because I have an extreme example. We have a coal mine and we want to measure some humidity in the mine. I don't know, 10 kilometers down into the center of Earth, you have some kind of sending unit and your receiver is sitting on top, on the outside, on the surface in this case. So of course, we always speak about ground as this 0 volt potential, but is it really 0 volt? Well, in an ideal world, yes, but electronic engineering is never ideal. So you probably have a difference. A difference in voltage will create a current. Yeah? So in this case, maybe you should switch to something else. Yeah? Maybe shielded is not, maybe one sided shielded is better. Or you go completely glass fiber connections, or what else. Yeah, that's one thing. And that's not a fairy tale, but it really happened. We had that exact example in Austria, where we had a customer who was attaching the shielding on both sides, and he was failing the EMC test. He opened the shield on one side, and he passed the EMC test. For that customer, shielding on one side was way better than on both sides. But you have to be aware that sometimes the answer to your praise is also to understand what you did. And to explain what maybe happened is also this example. I bought a really cheap VNA, nano VNA in this case, 200 euros on, I don't even know, I think Amazon. And I made a Smith chart measurement of a coaxial cable. So we have on the right side the open circuit, we have short circuit, and we have 50 ohm. Huh? I only attached the cable on one side. So you would think that the cable should always stay on the open. But it clearly doesn't. With increasing frequency, at a certain point, there is a short circuit. This short circuit is exactly at lambda divided by 4. This is the spot where there is the highest impedance transformation. An open becomes a short. But what does that matter for our application, or in this case for our example? Well, you have an inner conductor, you have in this case a capacitance, you have an inductor. You also have, due to your shielding, a capacitance. So what did you create? Well, a low-pass filter. In this case, for the customer, it was ideal because that low-pass filter was filtering out all of those noise. Because shielding is, of course, only going to shield something. It will not have filter properties. Yeah? So if you have noise on one side, it probably will travel to the other side. But then again, it's not the fault of the shielding, but better you have to look at the source of the noise. It's a bit like in the morning I told everyone, yeah, you have a headache, you need pills against headache. That's one way to solve the issue, or the other way would be to check why you have a headache. Maybe you are wearing a hat that's really small, and that's the case why you have a headache. Why is that a problem? I mean, yes, of course, it's not a real life example because it's really a simple version. But what happens if you change the length of your cable? Well, lambda divided by 4 will also change because the properties of your cable changed. You have a higher capacitance, you have a higher inductance, therefore you have your frequency or cutoff frequency, a resonance frequency in this case, somewhere higher or somewhere lower. So maybe you pass your EMC test with a cable length of 152 millimeters, but are you sure that you are still passing the EMC test with 2000 millimeters? And are you even aware that changing the length is maybe affecting your overall measurements at all? Those are those things where there's a high chance that you stumble upon small issues or create issues for the future. Yes, that's all from my side. We are now in the part where you are actually allowed to ask questions. In this case, my colleague is going to come with the laptop. As in my age, I won't be able to read any questions from this distance.
Perfect. First of all, thank you very much, Dominik, for the very cool presentation and all the interesting facts we just heard. And also thank you very much for your attention. And I see there were also a lot of questions coming in. And yeah, we just now have the time to go through them. Also, the questions came up, will the slides be shared and also the recording of this webinar session? Yes, both of them will be shared, and I will also quickly start with the handout. So you should now be able to download this as well. Okay, but now let's go on with the question.
A small side note, we did not tell the audience that, or did we share the app note?
Yeah, I shared it in the meantime.
Okay.
Yeah.
Because I already saw some questions regarding how to choose the capacitance. And there is no really easy answer for that question. Again, it's application depending and also signal depending. But regarding Ethernet, we have now a pretty big app note regarding that, where we can see tips from the internet compared to the things we would suggest, and compared to a completely attached shielding. Yeah.
Okay, so then let's just dive into the questions. I would like to learn more about PCB tracing techniques.
Yeah, that's a superb thing. We are currently working on a few really nice experiments to show a few things, what are things you should avoid more, and what you can do to increase your signal integrity, meaning reduce the impedance mismatch by a lot.
Okay, thank you very much. So then, next question. Yeah, how can you tell if coupling is due to an electric field or a magnetic field?
There is a rather easy thing you could do because that's a material most of you guys have probably at home. It's aluminum foil. Yeah, if you wrap it around your application or maybe your suspected noise area, and the coupling is being reduced by a lot, or you attach some kind of shielding, you are pretty sure that it's an electric field, which is also the best thing that can happen because that's quite easy to shield. If it's magnetic, it's going to be quite more tricky. You have to either increase the distance or use specific materials with a higher permeability, in this case ferrite sheets or flexible ferrite absorbers and whatnot, to try to mitigate those emissions.
Okay, thank you very much. So then, next question is regarding page number 33.
Yeah.
Could you explain
the part of the layout suggestions for USB 4 lines to 6 lines, page number 43. Probably the easiest version is going to be I will directly answer you per email, because then I can show you more than there is in this presentation regarding these matters. So you can see all the calculations and the measurements and also the topology and the idea behind, if that's okay for you.
Okay. Yeah, also there, the hint from my side. If we can't answer all your questions now in this live webinar, then just reach out to us. And also the open questions, we will answer them later on via email. Or Dominic will do it.
It's going to be my work now. Great.
Okay, then we can move on. How can I recognize a well-shielded cable?
There is sadly a universal truth about shielding, and it's that you will not see the quality from the outside, and you will not see the quality by just increasing the overall cable costs. What do I mean by that? Even we as Würth Elektronik failed with shielding quality because we did our app node and we created measurements. And what we saw was that we had some spikes and we were over the threshold, and we found out that it was the poorly shielded USB cable. How did we find that out? We used X-ray to look into the connector, and we saw that it was connected with a pigtail. So just with one simple strand of the shielding directly soldered onto your casing. In this case, the easiest thing is order more than one cable and cut them open and look if the overall material is more than 95% and the attachment is done by at least 360 degrees, or ideally soldered in a 360 degrees area. That's the easiest way to find that out. But yeah, it's manual labor, sadly.
Yeah, sometimes life isn't easy.
Yeah, sadly it's always on your responsibility to cut it open. So be aware of that.
Okay, thank you very much. Then we go on with this one.
Yeah, that's exactly the question I was referring to. How do you choose the size of the capacitor in the two-ended shielding? I talked with different electronical engineers in different areas, from the automotive part to the industrial part. Really hard, because then it's more a religion than anything else. In the automotive part, what I often heard is, don't use one capacitance, use 3 capacitance with different resonance frequencies, so you catch more than one of those noises that might go over the ground plane. With Ethernet, we have the suggestion from Würth Elektronik side that I think it was a 10 nanofarad on both sides. What I can also tell you is, when you choose a capacitance, ideally, when you connect it to your circuit board, do it on the top and on the bottom, so it's always symmetrically. Because if you only attach it on one side, it's not that good. But again, that's also seen in the app note, where you see real life measurements regarding that. So yeah, that's my not so conclusive answer for your question currently.
Okay, thank you anyway. Okay, then next question here. What is the best way of connection the shield of connector? Decoupling caps, TVS or anything for between ground, earth and connection?
Yeah, that's the next thing. Well, the best way, if we look purely on the measurements we did, directly connecting is always the best. Again, if the application allows it. For certain cable length, if you are, I don't know, longer than 10 meters or 20 meters, maybe a capacitance is going to be needed. So if you have a spot on your circuit board where you could place some kind of layout where you can put them on later, that would be ideal. TVS diodes is also a thing, because in our application note regarding shielding, we did not only use capacitance, but also we did use, I think, a resistor, but I'm not completely sure, where we also reduced the transient that may occur on the shielding. Yes, and for between ground and earth connections. There's one last recommendation you can often see, is that regarding PE or protective ground, that should also be connected near where the cables are going to enter your casing. That's another small additional tip you can use.
Okay.
Yeah.
So then, regarding the time, we see we are already a little over it, but we take still the time for the last question. So yeah, what's the recommendation for virtual ground? Separate polygon or complete layer for each ground?
Yeah.
Polygon.
The next thing regarding ground planes is, that's the biggest minefield of them all. Depending on who you ask, some will say, yes, you should never separate ground planes by any means. We also have, to be honest, some circuit boards where we see a good design and a bad design of, I think it was a DC-DC converter, where we really use a separate low noise filter ground of sort. But in most cases, if you separate something, that's not a good idea, only if you really know what you do. And that's often really hard to see or hard to guess what's going to affect. So yeah, that's one of those cases where I would be really hesitant to give any tips. It's a bit like the thing where what we get asked quite a lot is, what should be directly under power inductor? Should it be a complete fully ground plane? Should it be, I don't know, no ground plane? Or should it be those, what is it called? I don't even know the English word for it. It's a grid system, yeah, where you have more than one line. But also that thing we can answer if you have questions regarding that matter.
Okay.
Superb.
So then I would say we are already at the end
Yeah.
of our webinar. Thank you very much for your attention. And yeah, I hope you enjoyed the webinar. And Dominic, thank you again for the time.
I say thank you for inviting me to Germany.
Yeah, you're very welcome.
Super.
So yeah, then I hope you stay tuned with our webinars. We also have a lot of other webinars online. Just look on YouTube or directly in our video center. We also will link maybe referring another webinar which is about EMC. And yeah, then I wish you a good day and goodbye.
Bye-bye.